Hi, I was going to make a calculus video for lesson 1-1 to help people who have missed class or just need some extra help. So for lesson 1-1, it's titled A Preview of Calculus, and there are some good examples in the PowerPoint. So I would suggest going over the PowerPoint that's posted on Canvas too, but we'll go over a few things here and some example problems that will help you. So the PowerPoint talks about calculus as being the mathematics of change. Okay, so we want to get an idea that if you have an object traveling at a constant velocity, you can analyze that kind of problem with pre-calculus. But if the velocity is changing, you need calculus to do the problem. So that's some keywords to look for when you look at story problem stuff. Look for constant velocity. That would be a pre-calculus concept. But if the velocity is changing, you'll need calculus to solve. Okay, so an example to go through together would be something like this. Find the distance traveled in 18 seconds by an object traveling at a constant velocity of 25 feet per second. Now, a velocity is a rate of speed, and there's those words, constant velocity. If it says constant velocity, you should recognize that this is a pre-calculus problem, and it's something simple, and it goes back to distance equals rate times time. They want you to find the distance traveled. So it's just a distance equals rate times time problem. They give you the time, 18 seconds. They give you the rate, because a velocity is a rate of speed. They give you the rate, 25 feet per second. So you simply plug those numbers in. We don't know the distance. We're trying to find the distance. The rate is 25 feet per second. The time, they gave you 18 seconds. Now you see here I wrote those labels on the numbers, 25 feet per second, it's like feet over seconds, times 18 seconds. And I want to point out that this year we're going to need to watch our labels on our questions, and the seconds would cancel out because it's feet over seconds times seconds. So the word seconds cancels out. And then you're left with the label, the answer's in feet, the distance is in feet, times those numbers, and you get 250 feet. Okay, so that was a pretty simple one. And there'll be a few like that you'll notice on the assignment. They'll just be pre-calculus, some concept you know, distance equals rate times time. Okay, now the next one, another problem here, could be something a little more complicated. This one says, find the distance traveled in 20 seconds by an object moving with a velocity of v of t equals 25 plus 6 sine t feet per second. So unlike the last one said constant velocity, this question, the velocity on this one is a function, and this function would be a changing value. This is not a constant velocity. We know the sine curve goes up and down and changes. So this is a calculus problem, and I've just drawn the sine curve here to kind of review and remind you that would be a changing velocity because the sine curve oscillates up and down. So this part of the problem where it says sine t, that sine value, if you think about it, that sine value will change. And if you remember about the sine curve, the highest the sine curve, if you just are thinking of the normal sine curve, the highest it goes is 1, and the lowest it goes is -1. So the part of the problem that has this sine sine t, that part of the problem, that will be a value between 1 and -1. And it would keep changing throughout the problem. So it is a calculus problem, so we want to try to estimate this and do it the best we can. We have not learned a lot of calculus yet, but we're just getting into it. So we just know that it's a changing problem, so it's a calculus concept. So if you think about it, what is the fastest this object could be moving? If the sine was at that maximum value of 1, if this sine value part here was 1, then it would be 6 times 1 right here. And so I've kind of written out off to the side, it could be the fastest this object could go could be 25 plus 6 times 1. And that comes out to 31 feet per second. The fastest this object could be traveling would be 31 feet per second. But like we said, the sine value could change. What if the sine part came out to be -1? And then it would be 6 times -1. So then the object wouldn't be traveling quite as fast. It'd be 25 plus 6 times -1, and it would be traveling at 19 feet per second. That'd be the slowest it traveled. So this value of how the velocity is going to be changing between 19 and 31 feet per second. So since it's a calculus problem, we're trying to just estimate this. So let's just get an average rate of speed. The speed is changing throughout the problem. The fastest this object could go is 31. The slowest this object could go is 19 feet per second. So I just took an average of those. 31 plus 19 divided by 2. The average is 25. The average speed is 25 feet per second. And some students were noticing it's the same as the beginning of that problem, 25, because it's like 25 plus 6, 25 minus 6, so the average is 25, right in the middle. So an average rate of speed is 25 feet per second. And like we said, this rate is changing throughout the problem. This velocity is changing. So we're just going to use an average there, put in the 25, and we're just going to do the best we can and figure out the average of this problem. So 25 times the time, which was given up above, 20 seconds, and 25 times 20 comes out to 500. So, and that would be an average, an estimate. So we know it's a calculus problem. We know the velocity is changing. We do the best we can. We estimate it for the purpose of this assignment. So we get distance of 500 feet. Okay, now I have one more problem to show you. Here, we'll just flip this over. Okay, one more problem to give you an example of some other kind that you might encounter as you do your assignment today. Another example would be a skier is riding on a path modeled by this function f of x equals 2 times the quantity 5x minus x squared. Find the rate of change in elevation at x equals 4. So now I've written here underneath rate of change in red, tried to highlight that a rate of change is a slope. You know, like a slope of a line is a rate of change of the line. So rate of change, when you see that in a problem, they're looking for a slope. Now this problem, again, is a difficult problem that will require calculus. And I suggested in class that students look at this graph. So we went to that website desmos.com and we graphed this just so we could get an idea of what this picture looks like. So here I'm going to cover this up. Or maybe I'll just write it again for the purpose of this. So, because we wrote this out in class, so I want you to get an idea. So I used desmos.com to just get an idea of what this graph looks like. If you plug in some numbers, that's another way. You could make a table and plug in numbers and get values. If you plug in 0 for x, you get 0. It's 0, 0. But like I said, I just went on Desmos.com and I got a pretty good picture of what this thing looked like. So I'm going like 2, 4, 6, 8, 10, 12. This thing was a curve. This is a parabola if you graph it, and it's a curve, and it went up. Again, I just got this off of Desmos.com just for speed, just to graph it real fast. So this graph basically looks like that. And they want you to find the rate of change in elevation at x equals 4. When x equals 4, you're up here somewhere. Now your textbook says if it is a calculus problem, that you should try to figure out the answer graphically or numerically. So the graph helps us kind of visualize this. But we have this problem, this graph. We have this f of x. F of x, you could write y also for f of x. So I'm going to write y equals 2 times 5x minus x squared. Okay, there's the formula they gave us. Find the rate of change in elevation at x equals 4. Okay, so here and here, what if I plugged in 4? So I'd have 5 times 4 minus 4 squared times 2. Let's figure out the math here. Let's figure out this point. 4 comma what? So you could grab a calculator and figure this out. I got 8. So I'm getting the point 4.8 right here. 4.8. They want you to find the slope at that point 4.8. The rate of change, it's like the slope. Slope, so if you make a line right there, the slope of the tangent line right there we want that rate of change, that slope right there. Well, we might need some more points off this graph to find a slope. So I suggest try some more numbers. We got 4 comma 8, okay? What if you tried the point 3 in there? So what if we tried 5 times 3 minus 3 squared? Let's get another point on this graph. 3 comma what? Okay, again, grab a calculator, do the math. If you plug in 3 for the x, if you plug in 3 for those x's this time, if you plug in 3, you get 3 comma 12. This one was 4 comma 8. So I'm getting a point up here, 312. So if I find the slope between 312 and 4.8, that's an estimate of the rate of change up here on this graph, on this hill. You're on a ski slope. It's a skier on a path. So if I do the slope, that's what rate of change is. It's a slope. So if I do the slope and do y2 minus y1, so 12 minus 8, and 3 minus 4, I would get -4. I would get a slope of -4. So the question is that the best answer we could get? Well, the PowerPoint talked about the tangent line problem. You know, 312, that's a whole unit away from 4.8. 3 to 4, that's quite a ways away actually. You could actually even get really, really close to 4 and get a better estimate. So we have the point 4.8, and we're trying to find the rate of change at x equals 4. So you need to pick another point that's really, really close to 4. Like how about 4.001, something really, really close to 4, and find the slope there. between those points. So grab a calculator, and for the x in the problem, plug in 4.001 and do the math. And we did that earlier, and we got 7.994. That's really, really close to 4, and that'll be a really good estimate of what this rate of change is at x equals 4. So do the slope again. Do 7.994 minus 8 and 4.001 minus 4. Let's figure out the slope here. If you do the math and subtract those and find the slope, you get -6. And that would be the best estimate. That would be a really good estimate. The answer for this problem could be a slope of -6. That looks more accurate because see, this was more slanted. That's only a slope of -4. If you get really, really close to 4 and pick a point really, really close to 4, that is a good estimate of the rate of change at 4.